All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. This is an AP Chemistry, and I'm going to be finishing up topic 6.1, which looked at endothermic and exothermic processes. And we're going to be picking up where we left off with enthalpy and talking about state functions, because what we're going to find is that enthalpy is a unique property that's known as a state function. So let's go ahead and dive right in. So usually when we think about internal energy and even enthalpy, we have no way of knowing the actual amount of internal energy of a system. The reality is that's just simply too complex of a problem for us to be able to break down. But here's what we do know. We do know that the internal energy of a system is independent of the path by which the system achieved that state. That sounds really complicated, all right? And I want you to think about it from this perspective. You've got this diagram at the bottom where you've got your kind of final state is the water, the liquid water, 50 grams at 25 degrees Celsius. Now, the reality is there are multiple different ways that we can get to a final state of 50 grams of water at 25 degrees Celsius. And so one way we could have done that is we could have reached that by simply cooling 50 grams of water that was at 100 degrees Celsius. So energy would leave this system and go into the surroundings so that it eventually gets to an internal energy that's equivalent to 50 grams of water at 25 degrees Celsius. Likewise, we could also achieve that same state by going from 50 grams of ice at 0 degrees Celsius. It warms up and it moves to a state. Energy is added into it so that its internal energy matches that of the water at 25 degrees Celsius. So it's like, okay, what are you saying, Mr. Kenton? Why is this idea of state functions, this idea that the path that can get there from multiple different paths? Actually, that's going to provide us the method for which we can actually calculate internal energy or even enthalpy, because both of those things are state functions, right? So internal energy is a state function. And so what that means is that it depends only on the present state of the system. Doesn't matter how we got there, right? So at the end of the day, all that matters is if you know the initial conditions and if you know the final conditions, because as long as you know those two pieces of information, you can figure out delta E. It doesn't matter if you started out at 0, went to 100, and then went back to 50. The only energy that would matter was your initial and your final, right? So just kind of keep that in mind. Our state functions are solely based on the initial and final conditions, not whether or not you go back and forth, do it 4 times, just initial, final conditions. That's all that matters. Now, within that, if internal energy and enthalpy are state functions, it's important to recognize that Q and W are not, right? It does matter where heat is moving or what work is being done. It's traveling in a specific direction. Like the final and initial states of those things, it does matter if we go up and down and back and forth, right? And you can think of it from this particular perspective. You've got 2 different batteries, and the way they get discharged, they lead to the same delta E. Right? This particular battery, it's attached to probably a light bulb. You're losing a bunch of heat and light energy, right? But here, in the fan example, you've got energy that's going to be lost as heat, and you're going to have energy that's being lost in the form of work that this fan is doing. Now, with the battery, it's still lost the same amount of energy, right? Because the path, it still ended at the same point. But the way we got there was unique. Right? And so keep that in mind, that although internal energy is a state function, Q and W are not. All right? Which leads us to endothermic and exothermic processes. And again, what we're looking at here is we're assuming that we're at constant pressure. So an exothermic process is when energy gets released. And so in that case, what we're saying is that heat energy, thermal energy, is being transferred into the surroundings. So delta H is going to be negative. Now, something's going to be endothermic when energy is absorbed by that particular process, so the system is taking in energy, and that means it's going to have a positive delta H, okay? And again, I think that should be pretty straightforward for us, which is going to lead us into enthalpies of reactions, right? Because we know that during the course of a chemical reaction, sometimes there's some pretty significant energy changes that happen. And so the change in enthalpy, delta H, is going to be the enthalpy of the products minus the enthalpy of the reactants. Sounds a lot like internal energy. Energy final minus energy initial. So delta H is going to be the enthalpy of the products minus the enthalpy of the reactants. And of course, depending on the reaction, like here, what we've got, if we've got CH4 plus O2 reacting to make CO2 and H2O, well, that's going to release 890 kilojoules of energy. If we've got carbon dioxide and water reacting to form methane and oxygen, well, that's going to take in 890 kilojoules of energy, right? It's kind of a unique property that we're going to see over time is that when you reverse chemical reactions, the energy change that takes place simply has the opposite sign of the original process. But looking at this, enthalpy, the change in enthalpy is going to be the enthalpy of the products minus the enthalpy of the reactants, okay? Now, this quantity delta H refers to the enthalpy of the reaction, or it can commonly be referred to as the heat of the reaction, right? And so in this particular process, we've got hydrogen and oxygen reacting to form 2 moles of hydrogen plus 1 mole of oxygen, making 2 moles of water vapor. And we can see from the enthalpy diagram, or kind of the very simple energy diagram, that the reactants released energy, and so it's an exothermic process. All right, now here's some things that we need to consider about enthalpy. Enthalpy is an extensive property, and what I mean by that is that it's going to be determined, or it's going to be based off of how much you have, right? Because think about it from like a chemical reaction standpoint. If a reaction can release a certain amount of energy, if we put it in the perspective of moles, if I have 2 moles of it, well, that means I have twice as much. So that means that I can release twice as much energy. So it matters how much stuff we have that we're dealing with. Now, delta H for a reaction in the forward direction is going to have the same value, but opposite sign to the delta H for the reverse reaction. You could think of it as the reverse reaction has the opposite sign of the forward reaction, right? And again, delta H for reaction is going to depend on the state of the products and the state of the reactants. So physical states are going to play an important role here. All right, and that, ladies and gentlemen, is going to wrap up our video. Thank you so much for joining us. When we come back next time, we'll look at energy diagrams. It should be a quick review since we hit these in kinetics. Thank you guys for joining me, and I'll see you guys again soon.